So Duguay's theorem is the idea that if you have a tetrahedron that has a corner whose sides meet at right angles to each other on all of the faces. So basically, if you have a tetrahedron that has one corner that's the side of a cube or the side of a rectangular prism, for example, that the area squared of this triangle that's sort of falling into the rectangular prism, that triangle's area squared is going to equal the square of this triangle's area plus the square of this triangle's area plus the square of this triangle's area. And the way we show this is using something called Heron's formula. And Heron's formula is that if you have any triangle, so it doesn't have to be a right triangle, just any triangle with sides A, B, and C, then the area of that triangle is going to equal the square root of something called S, which we'll explain in a second, times S minus A times S minus B times S minus C. But because we're looking for the area of this non-right angle triangle squared, we can write the formula this way. And this is where S is just a shorthand way of writing a half A plus B plus C. So that gives us our area for this face squared. But if we want this face squared plus this face squared plus this face squared, we can do it as well. It's just that we're going to need to use Pythagoras' theorem. Sorry, not Pythagoras' theorem. We'll just use base times height. So the area squared is just going to be, or rather the area is added together squared. It's just going to be a half F times D squared plus a half E times D squared plus a half F times E squared. And that comes out as a quarter F squared D squared plus a quarter E squared D squared plus a quarter F squared E squared. So now that we have the formula for each of these, we can compare the two. But we run into a problem in that the elements that go into this formula, basically A, B, and C, and a constant, but it's A, B, and C that are the problem. A, B, and C are not written here. And here is not written F, D, and E. And we need one of those things to be re-expressed as the other. We need A, B, and C to be re-expressed as F, D, and E, or F, D, and E to be re-expressed as A, B, and C. But we can do it because we can notice that A, B, and C are the hypotenuses of these right triangles whose sides are F, D, and E. So we can notice that A is going to be the square root of F squared plus D squared. we can notice that b is going to be the square root of e squared plus d squared. We can notice that c is going to be the square root of f squared plus e squared. So having done that, we can plug all these into here and into here finally, but that's going to be a lot of working by hand, so I would rather do that through Wolfram Alpha. So we have that this is equal to this, and we can see that these are equal. So this is equal to this, which means that the area squared of this side is equal to the area squared of this side plus the area squared of this side plus the area squared of this side, which means that Degua's theorem is true.